You know that feeling when you're trying to stay on top of just a mountain of information, especially in the, well, lightning fast world of software delivery.
Oh, absolutely.
It can feel like you need some kind of superpowered shortcut,
Yeah.
right? To really get to the core of what's working now without getting totally lost in the jargon.
Yeah, cutting through the noise.
Well, you're in the perfect place. Today, we're taking a deep dive into something truly foundational, something that's totally transforming how software gets built and delivered.
CI/CD.
Exactly. Continuous integration and continuous delivery or deployment. It's a set of practices that doesn't just promise speed, but also, you know, rock-solid stability and reliability, too.
Which are crucial.
Think of it as the secret sauce for getting software from just a brilliant idea to your user's hands, quickly and consistently, all while making sure the quality is there.
Our mission today, really, is to unpack the essential best practices that make CI/CD truly transformative for, well, any organization. We'll go beyond just defining the terms.
Right.
We want to explore the why behind each core principle, how these practices fit together like puzzle pieces, and what tangible, measurable benefits they actually deliver.
Okay.
We've pulled some truly insightful nuggets from the sources you provided, and we'll try to highlight not just the what, but also the so whats for you, our curious listener, aiming for those aha moments of understanding.
Fantastic.
Fantastic.
So get ready to discover how automation, some pretty profound cultural shifts, and strategic tooling can revolutionize software delivery. We'll be covering, well, everything from its core principles and business benefits to the practical architecture of a robust pipeline.
The nuts and bolts.
The unsung hero of version control, crafting perfect builds, managing those critical software components,
Yeah.
comprehensive testing that truly builds confidence,
Yeah, confidence down.
advanced deployment strategies that minimize risk, defining your infrastructure as code, embedding security with DevSecOps, and finally, that crucial role of monitoring and observability. Seeing the whole picture.
It's a big landscape.
It is. It's a comprehensive look designed to give you that sharp, clear understanding. Okay, let's start right at the very beginning then. CI/CD. Continuous integration and continuous delivery or deployment.
Yeah.
It's more than just a catchy buzzword these days, isn't it? It seems foundational in modern software development. But what does that actually entail? Like day to day?
Right. At its core, CI/CD is fundamentally about automating things. Automating builds, automating comprehensive testing, and enabling frequent deployments.
Okay.
It's a systemic approach designed to streamline and accelerate the entire software development lifecycle, from the moment a developer writes code to the moment it's live in production. But it's really vital to grasp that its significance stretches far beyond mere automation. Like, just installing a CI server, say Jenkins or GitLab CI, isn't going to magically get you there.
Right. It's not just a tool.
Exactly. The true value of CI/CD emerges from the cultural and the process transformations it instigates. It's about fostering a culture of speed, stability, and reliability qualities that are absolutely paramount in today's rapidly evolving digital landscape.
A culture shift.
A big one. It's about teams embracing practices like frequent small code commits and taking shared responsibility for the entire delivery pipeline. The tools, they act as catalysts, helping to enforce these desired DevOps behaviors, like requiring automated tests to pass before any code can be merged into the main branch.
Okay.
But without this holistic approach, just focusing solely on the technical tools will significantly limit the benefits you can achieve. You won't get the full value.
Okay, that makes sense. So let's unpack this a bit more. We hear CI, continuous delivery, continuous deployment. They sound similar, almost interchangeable sometimes,
They do get used interchangeably, yeah.
but they represent different levels of maturity and automation. Can you walk us through that spectrum from the starting point to, I guess, the ultimate goal?
Absolutely. Think of these terms as a progressive journey, maybe a continuum of automation and maturity in how software gets released.
Okay.
First up, we have continuous integration, CI. This is really where it all begins. It's the bedrock.
The foundation.
Exactly. It's a practice where developers frequently, often multiple times a day, merge their code changes into a central shared repository. Like, imagine everyone constantly collaborating on a single shared whiteboard.
Right.
Each time someone adds a new idea, or in this case code, it's immediately reviewed and checked to ensure it integrates seamlessly with everyone else's work.
So constant checking.
Constant checking. In the CI world, each integration is automatically verified by an automated build process and a suite of fast automated tests. The primary goal here, catch integration issues early.
Super early.
Yeah, thereby minimizing the complexity of merge conflicts later on and ensuring the main code base is always stable and buildable, always healthy. This constant validation means the core code is continuously in a healthy state, always ready for the next step. And by minimizing the bureaucracy and overhead associated with code integration, CI enables engineering teams to scale more effectively.
How so?
Well, both in terms of team size and the complexity of the code base, because you're not waiting for these massive, painful merge conflicts down the line. You avoid that merge hell.
Ah, yes. Merge hell.
It's like brushing your teeth daily to prevent major dental problems later. Small, frequent actions.
Got it. So building on that solid CI foundation.
Right.
What's next?
The next step is continuous delivery, CDL. This practice automates the release of software that has successfully passed all the automated tests.
All of them.
To production-ready environments. Now, the key distinction here is that while the technical process of preparing a release is fully automated, the final decision to actually deploy to the live production environment often remains a manual step.
Ah, okay. So it's ready, but someone pushes the button.
Exactly. That decision is typically driven by business considerations. Maybe there's a marketing campaign to launch alongside it or a specific business quarter target to hit.
It makes sense.
So think of it this way. Your software is always ready to go. It's packaged, thoroughly tested, and basically sitting on the launch pad waiting for the final go signal from mission control, which is usually the business side.
Right.
Continuous delivery ensures that the software can be released to users at any point in time, providing significant business agility. It truly decouples the technical capability to release from the strategic business decision to actually release.
So you can react faster.
Instantly. You have the power to react to market changes or new opportunities immediately without that mad scramble to prepare the software last minute.
Okay, so that's continuous delivery. What's the final stage?
And finally, we reach continuous deployment, CDMT. This is the ultimate stage in the CI/CD continuum, the highest level of maturity and automation. Pretty much. With continuous deployment, every single code change that successfully passes through all stages of the automated CI/CD pipeline. And crucially, this includes all tests, from unit to end,
Every single one.
is automatically deployed to the production environment with no human intervention.
Wow, fully automated.
Fully automated. There is no manual go button. If it passes the automated gauntlet, it ships. This approach maximizes the velocity of releases, allowing for incredibly rapid iteration and getting new features or bug fixes into users' hands almost immediately.
Sounds amazing, but maybe a bit scary.
It demands an exceptionally high level of confidence in the entire automated pipeline, particularly in the thoroughness and reliability of your automated testing and the robustness of your automated rollback mechanisms. You're effectively trusting your automation implicitly.
Ironclad automation.
Your testing and safety nets must be absolutely ironclad because your system is truly autonomous at that point.
So aiming for that kind of automation and agility,
Yeah.
what are the guiding stars, the fundamental principles teams should follow?
Yeah, there are several fundamental principles that act as guiding stars, truly shaping how successful teams implement CI/CD.
Okay.
First, automation. We've touched on this, but it's the cornerstone. Automating builds, testing, deployment processes. The goal is simple. Reduce manual effort, minimize human error potential, and significantly increase speed and consistency.
Let the machines do the work.
Let machines do the repetitive, predictable work so humans can focus on creativity, problem-solving, innovation. Free up your people.
Right. What's next?
Second, frequent integration in small batches. Developers commit changes early and often in small, incremental batches. Think building a wall brick by brick, checking stability constantly instead of lifting a massive section.
Yeah.
This makes bugs much easier to find and fix, simplifies merging, and drastically reduces the risk of those large, infrequent integrations that often lead to.
Merge hell again.
Exactly. Those multi-day conflicts, untangling that giant ball of yarn. Avoid that.
Makes sense. Principle number 3.
Third, fast feedback loops. This is crucial. A key objective is giving developers rapid feedback on their changes. Automated builds and tests run quickly after each commit, immediately telling them if there's an issue.
So they can fix it straight away.
Right. It prevents small bugs from growing into complex, costly problems later.
Yeah.
You want to know within minutes, not hours or days, if your change broke something. Fix it while it's fresh.
Okay. Principle 4.
Fourth, version control everything. Not just your application source code. Everything needed to build, test, and deploy.
Like what?
Build scripts, test scripts, deployment configurations, even infrastructure definitions, infrastructure as code, which we'll get into, all in a VCS like Git.
Why is that so important?
It creates an auditable history, enables seamless collaboration, ensures consistency. It's your single source of truth for everything about your software and its delivery.
Yeah, single source of truth. Number 5.
Fifth, build once, deploy many. This is fundamental. An artifact like a compiled binary or a Docker container image.
The thing you built.
Yes, the thing you built. It should be built only a single time during the CI process. Once built and verified, this same immutable artifact gets promoted through dev, test, staging, and finally, production.
Immutable meaning it doesn't change.
Exactly. It guarantees that what was tested is precisely what gets deployed. No, it worked in staging. Why is it broken in production? Moments caused by rebuilding.
Ah, that dreaded phrase. Okay, and the last principle.
Finally, consistency across environments. Development, testing, staging, production environments must be consistent, as close as possible.
Why?
Because discrepancies, different library versions, different config settings are a super common source of frustrating deployment failures. It's where the "it worked on my machine" problem really lives. CI/CD, especially with ISE, aims to make environments identical. Predictable path to production.
Got it. Now, this sounds like a significant investment, a lot of work to set up and maintain correctly.
It is an investment, yes.
So what are the actual benefits? What does it really do for the bottom line beyond just being technically elegant?
Oh, the benefits are substantial and, crucially, measurable. They go way beyond technical efficiency into real business growth and competitive advantage.
Okay, like what?
Firstly, a huge increased speed and development velocity. Organizations doing CI/CD well deploy way more often and have dramatically faster lead times.
How much faster?
The data from DORA, the DevOps Research and Assessment Group, is compelling. High performers deploy 208 times more frequently and have a lead time 106 times faster than lower performers.
Oh, that's staggering.
It's a massive competitive advantage, responding to market demands almost instantly. Think how much faster you can innovate.
Okay, speed is one. What else?
Secondly, improve stability and reliability. Continuous automated testing ensures code bases stay stable and release ready. Issues get caught early and often, so the overall quality of software going out is much higher. Fewer production incidents.
Makes sense.
Which leads naturally to enhanced code quality. Early bug detection means issues don't fester and become complex, costly problems. Developers get immediate feedback, fix things when the context is fresh, encourages cleaner code.
Good point.
There's also reduced risk. Deploying smaller, frequent changes is inherently less risky than those big bang releases that can break everything.
Less riding on each deployment.
Exactly. If something goes wrong with a small change, the impact is minimal. And automated rollbacks add a safety net.
And what about the teams? The people?
You see better collaboration and communication. CI/CD pipelines promote transparency. Build, test, deployment statuses are visible to everyone. Fosters shared responsibility, breaks down those old throw-it-over-the-wall silos between dev, test, and ops.
More teamwork.
Definitely. And from a business perspective, it drives business growth and agility. Automating repetitive tasks frees up developers and ops. They focus on innovation, customer satisfaction, strategic needs, not manual toil.
So faster response to the market.
Much faster. You can react to market changes, competitor moves, new customer demands way quicker, literally outpacing the competition.
And finally,
it offers scalability. CI/CD practices and tools are designed to support growing teams, increasing code-based complexity, expanding infrastructure. It's a system built for efficient growth and adaptability.
okay, that's a compelling list of benefits.
Right.
Now, as with any technical field, there's specific terminology. It can feel like a whole new language sometimes.
It definitely can.
Let's make sure our listeners are up to speed on some key terms we'll be using a lot.
Indeed. Speaking the same language is crucial. 3 key terms are really foundational here.
Okay, what's the first one?
First, the CI/CD pipeline itself. This isn't just a concept, it's the automated workflow, the assembly line for your software.
The assembly line, I like that.
Yeah. It's a series of automated stages, build, test, deploy, that code changes pass through from commit all the way to production.
Yep.
It orchestrates the whole process, ensuring consistency and automation at every step. Predictable, repeatable delivery.
Got it. Pipeline, what's next?
Then we have DevOps and DevSecOps. DevOps is that cultural and professional movement emphasizing collaboration and automation between development, dev, and operations.
Ops, bridging the gap.
Exactly.
Yeah.
CI/CD is a core set of practices that enables DevOps. You can't really do effective DevOps without robust CI/CD. DevSecOps then extends this by integrating security practices into every stage of the pipeline.
Kind of like a SecOps.
Right. Security isn't an afterthought, a last-minute check. It's a shared responsibility woven into the fabric of development and delivery. Shifting security left, which we'll dig into later.
Okay, DevOps, DevSecOps, and the third term.
And this brings us to DORA metrics. This is where the quantification comes in, allowing objective measurement of performance. The DevOps Research and Assessment DORA-P team identified 4 crucial metrics, key indicators.
The vital signs.
Kind of, yeah. For software delivery and operational performance, there's deployment frequency, how often you successfully release to production daily, weekly, multiple times a day. Measures agility, lead time for changes, time from a code commit actually getting into production, measures pipeline efficiency, mean time to resolution, MTTR, average time to recover from a production failure, measures resilience, and change failure rate, percentage of deployments causing a production failure or needing immediate fixing, measures quality and reliability.
Those seem really important to track.
They are. The widespread adoption of DORA metrics is a significant evolution. It's a shift from just saying we release faster to objective, quantitative measures.
Data-driven improvement.
Exactly. These metrics help pinpoint bottlenecks, like maybe your lead time is way too long, and direct improvement efforts effectively. It compels organizations to treat their CI/CD pipelines not just as automation tools, but as critical systems needing continuous monitoring, analysis, optimization, just like production apps.
Treating the pipeline like a product itself.
Precisely. Understanding the real impact of your delivery process.
Okay, so every pipeline, like that assembly line analogy, it has a journey, right? What are the common stops, the stages that code takes from a developer's machine all the way to a customer?
That's a great way to think about it. Imagine this carefully orchestrated factory assembly line for your code. A logical progression of stages transforming raw materials into a finished product.
Okay, stage 1.
The first stop is the source stage. This is the trigger point, the starting pistol, usually activated by a code commit to a branch in your version control system, like Git.
So someone pushes code.
Yep. The pipeline then grabs the latest source code and any config files. Its reliability is paramount. If this gateway fails, nothing else happens, like the raw material truck never arriving at the factory.
Okay, source stage, then what?
Next up is the build stage. Here, your raw source code transforms into executable artifacts.
The actual software package.
Right. This involves critical steps, resolving dependencies, fetching necessary libraries, running linters and static analysis, catching early errors or style issues, and finally, packaging the application.
Into what kind of package?
Could be binaries, JAR files for Java, or increasingly common Docker container images. The goal here is a consistent, reproducible artifact. Any errors here need to provide immediate, clear feedback.
Fail fast.
Fail fast, fix fast.
Got it. Build stage. Next.
Then comes the crucial test stage. This is the primary quality gate. A variety of automated tests run here, unit tests, integration tests, maybe others.
Checking the quality.
Exactly. Validating correctness and quality. The thoroughness and speed here directly influence your confidence in the release. Flaky or insufficient tests erode that confidence, you risk deploying bugs.
Right. Impacts that change failure rate.
Precisely.
Okay, test stage, assuming things pass.
Once all tests pass, the journey continues to the deploy stage. Here, and the validated build artifacts are taken and deployed to various environments.
Like staging or production.
Could be staging for final checks or, ultimately, production. This stage often uses different deployment strategies, blue-green, canary, to minimize risk and downtime. Automation here is vital for consistency and reducing manual errors. Gets your software to users.
The final step.
Well, almost. We close the loop with the monitor stage post-deployment. After deployment, the focus shifts to observing the application's performance, health, user experience in the target environment.
Watching it in the wild.
Exactly. Collecting metrics, logs, traces, ensuring the new changes behave as expected. This provides invaluable real-time feedback, allows quick response to issues, and gives data for continuous improvement. Make sure your factory's products are actually working well for customers, truly closing that feedback loop.
That makes sense. Now, there are so many CI/CD platforms out there. Jenkins, GitLab, GitHub, Actions, Circle CI, cloud-native ones.
A lot of choices.
How do you take the right one? It must be more than just comparing features, right? Seems like a big strategic decision.
You're spot on. Choosing a platform is critical, it's strategic, it shakes your whole development culture, your innovation capacity even. It's definitely not just a feature checklist.
So what should you consider?
You need to align it with your existing infrastructure, your team's skills, your long-term goals. A misaligned platform creates friction, it doesn't streamline delivery.
Can you give some examples, like comparing a couple?
Sure. Take Jenkins.
Hmm?
Open source, incredibly flexible, huge plugin ecosystem.
The classic.
Right. Pro, customization. You can make it do almost anything. Con, can be complex to set up and maintain, often needs dedicated expertise, like a custom car needing a skilled mechanic. Ultimate flexibility, but operational overhead.
Okay, Jenkins, what about something more integrated?
GitLab CI/CD. Tightly integrated within the GitLab platform. All-in-one DevOps solution, source code, CI/CD, monitoring.
Everything in one place.
Exactly. Pro, that unified experience simplifies the tool chain. Easy for developers to go from commit to pipeline. Con, if you're not already deep in the GitLab ecosystem, it might feel overwhelming. It's comprehensive.
Right. And GitHub.
GitHub Actions. Native CI/CD within GitHub repos. Vast marketplace of reusable actions.
Very convenient for GitHub users.
Yeah, pro. Seamless integration if your projects are on GitHub. Feels natural. Con, potential for vendor lock-in if you rely too heavily on its specific features. Harder to migrate later.
Okay, and maybe one more, like Spinnaker. That comes up for complex setups.
Right, Spinnaker. Multi-cloud continuous delivery platform, designed for high-velocity, high-confidence releases. Natively supports advanced strategies like Canary, Blue-Green.
Sounds powerful.
It is. Pro, excels in complex multi-cloud scenarios. Sophisticated release control. Con, steep learning curve. Needs external tools for monitoring, usually. It's for organizations with high DevOps maturity and complex needs.
So the choice isn't purely technical then?
Not at all. It influences daily workflow, ability to adopt advanced practices like continuous deployment, even your cloud strategy. Integrated platforms like GitLab or GitHub Actions can accelerate CI adoption because the developer workflow is so fluid. Cloud-native solutions often encourage using other services in that cloud.
So you need a holistic assessment.
Absolutely.
Yeah.
Technical features, current DevOps maturity, team skills, cloud strategy, desired cultural impact, like fostering collaboration between DevOps and Sec. A misaligned platform creates friction, becomes a barrier, not an enabler.
Okay, version control. We all use Git or something similar. But what's its special, maybe even unsung role in CI/CD? It feels like more than just storing code, right? Almost like the central nervous system.
You've hit on a core truth there. It's not just storage. It is the fundamental backbone, the central nervous system, as you put it. Its importance really cannot be overstated.
So it's foundational.
Absolutely. A robust version control system, particularly Git, is where the journey of software delivery truly begins, and it's the anchor for your entire CI/CD pipeline.
Okay, how so? What are its key roles?
Well, first and foremost, it serves as the single source of truth. The VCS is the definitive, auditable repository for all code, scripts, configurations, documentation, everything related to the project. Everything. Every single change, no matter how small, is recorded. Provides a clear, immutable history. No ambiguity about what code is current or what version was deployed.
Got it. Single source of truth. What else?
Secondly, it enables seamless collaboration. Think about distributed teams today. Multiple developers, multiple teams working on the same code base concurrently. VCS provides the mechanisms to merge changes systematically, resolve conflicts. It's the traffic controller for your code.
Managing the chaos.
Pretty much, yeah.
Huh.
Ensuring everyone's work can be integrated effectively.
Okay. What's the third role?
Thirdly, it offers incredible traceability and rollbacks. Every commit tracks who made the change, when, and importantly why, through clear commit messages.
The audit trail.
Exactly. This detailed history is invaluable for debugging, understanding how features were implemented, compliance, and crucially, it allows easy reverts to previous known stable states if issues arise. That quick rollback ability is a core safety net in CI/CD.
Right. The undo button.
Your undo button. And perhaps most critically for CI/CD, it acts as the trigger for automation.
Kicking off the pipeline.
Precisely. In most CI/CD setups, a commit pushed to the VCS, or maybe a merge to a specific branch like main, is the primary event that automatically kicks off the entire automated pipeline. Build, test, deploy. Without this reliable trigger, your pipeline couldn't operate continuously. It's the signal that tells the assembly line to start.
Makes continuous integration truly continuous.
Exactly.
Okay, so within version control, there's this term trunk-based development, or TBD. It comes up a lot with high-velocity delivery. What exactly is it, and why is it considered so good for CI/CD?
Right. For high-velocity continuous delivery, trunk-based development, TBD, is definitely a recognized best practice. It aligns perfectly with CI/CD principles, and it's a powerful strategy for ensuring your code base is always essentially releasable.
Always releasable. How does it work?
At its core, the definition is pretty simple. All developers commit their changes directly to a single central branch, usually called the trunk or main branch.
Directly to main, no feature branches.
Well, long-lived feature branches where developers work in isolation for weeks are actively discouraged. Instead, you commit tiny, incremental pieces of a feature to the main trunk frequently, often daily, or even multiple times a day.
Small, frequent commits to main. What are the benefits for CI/CD?
Significant benefits. First, it embodies true continuous integration. The core CI principle of frequent integration of all developers' work into a shared mainline isn't just a goal, it's the daily practice. Almost completely eliminates that merge hell.
Okay.
Second, you get faster feedback loops. Small, frequent integrations mean automated builds and tests run super quickly, giving rapid feedback on codebase health. You know almost instantly if you broke something. Third, simplified merging and reduced conflicts. Frequent integration of small changes drastically cuts down the pain of large merge conflicts, like clearing small traffic jams constantly instead of letting them become massive pileups. And fourth, a key goal is maintaining an always releasable trunk. The code on the trunk should always be green or stable enough for production deployment. Huge business agility, always ready to ship.
It sounds powerful, but maybe risky committing straight to main. How do you manage that?
That's where some key enabling practices come in. They're essential.
Okay, like what?
First, develop in small batches. Work has to be broken down into small tasks, completable and integrable within, say, less than a day ideally, minimizes integration risk, makes code reviews much faster.
Right. Smaller chunks are easier to manage.
Exactly. Second, and this is absolutely critical, feature flags or feature toggles. This is a game changer for TBD.
How do they help?
New or incomplete features are wrapped in conditional logic. They get merged directly into the trunk, but remain dormant, inactive in production until you explicitly enable the flag.
So the code is there, but hidden.
Precisely. This is revolutionary because it decouples code deployment from feature release. You continuously integrate without exposing unfinished features. Plus, feature flags facilitate things like canary releases, A/B testing, granular control.
Very cool. What else enables TBD?
Comprehensive automated testing. Absolutely essential with frequent merges to the trunk. You need a robust suite of fast-running automated tests continuously validating stability. Without them, TBD would be incredibly risky.
The code reviews.
Efficient code reviews. The small, focused nature of TBD changes makes reviews much more efficient. Reviewers quickly grasp the context and impact. Faster approvals, higher quality.
Okay, so TBD sounds like the gold standard for high-velocity teams. But it's not the only way, right? How do other branching strategies compare, like Git flow or GitHub flow?
That's right, there are different strategies, and each has distinct implications for your CI/CD flow and delivery speed. The choice often reflects a team's DevOps maturity and philosophy on risk and release velocity.
So how does Git flow stack up?
Okay, Git flow. Description. It's highly structured. Multiple long-lived branches. Master for production, develop for feature integration, then feature release, hotfix branches.
Lots of branches.
Yeah. CI/CD suitability and impact. Offers a predictable release process, good for supporting multiple versions in production. But its complexity, with many branches and prescribed merge paths, can significantly slow down the dev cycle.
Why slower?
Because integration happens less frequently on those long-lived develop and feature branches, leads to larger, complex merges, merge hell risk, makes true continuous delivery challenging. Better suited for scheduled, less frequent releases, introduces friction.
Okay, so Git flow is more structured, maybe slower. What about GitHub flow?
GitHub flow, description, much simpler, more lightweight. Centered around a single main branch that's always deployable. New work happens on short-lived feature branches created from main. Changes merged back via pull requests for review before deployment.
Sounds faster.
It is. CI/CD suitability and impact. Simple, flexible, easy to adopt. Aligns well with CI/CD principles. Promotes rapid feedback. Frequent deployments because you're always trying to get changes into main and out quickly. Main is always release ready. Any downsides? The main challenge is ensuring those feature branches stay very short-lived to prevent merge conflicts. Discipline is key.
So the choice of strategy really reflects a team's approach.
Definitely. Gitflow suggests some more traditional risk-averse stance releases are big planned events. TBD and GitHub Flow embrace smaller, incremental changes. They manage risk through high automation, rapid feedback, prioritizing velocity.
And TBD with feature flags seems very advanced.
It is. The sophisticated use of feature flags in TDD allows decoupling code deployment from feature release, which is a hallmark of mature continuous delivery. So if you're struggling with CI/CD, your branching strategy might be an impediment. Moving to TBD, for instance, often forces improvements in automated testing and feature flag use, pushing teams towards greater overall DevOps maturity. It's a powerful forcing function.
Okay, let's talk about the build stage. On the surface, it sounds simple just compiling code, right?
You'd think so, yeah.
But I imagine there's a lot of nuance to doing it well. Doing it right seems like it could really accelerate the whole pipeline. What are the core rules for, well, excellence here?
You're absolutely right. The build stage is pivotal. It's where raw code transforms into a usable product, and its efficiency directly impacts the pipeline's speed and reliability. There's definitely a set of core best practices.
Okay, what's the first one?
First, automate everything possible. The goal is full automation compilation, dependency management, testing, packaging, deployment. Automation reduces manual toil, minimizes human error risk, increases speed and consistency. Build a predictable, repeatable assembly line. Free your team from mundane tasks.
Makes sense. What else?
Second, fail fast and fix fast. Design pipelines to detect errors ASAP. Syntax errors, failing unit tests should be flagged immediately, within seconds of a commit.
Quick feedback.
Crucial. Quicker feedback means faster fixes, lower cost. Know within minutes if something broke, fix it immediately.
Got it. Third,
Maintain a clean and consistent build environment. Every build must start from a known, pristine state. Prevents issues from configuration drift or leftover stuff from previous builds.
how do you ensure that?
Using containerization like Docker or virtualization is highly recommended. Create isolated, reproducible build environments that mirror production. Ensures reliable, consistent builds everywhere. Fights the "it worked on my machine" problem at the build level.
Okay. And the last core practice.
Finally, and this is a cornerstone, ensure reproducible builds. The ability to produce the exact same build artifact from the same source code commit every single time.
Why is that so critical?
Requires strict control over the build environment, pinned dependency versions, versioned build tools. Reproducibility is critical for debugging. You can reproduce the exact scenario and for reliable rollbacks. You're guaranteed the artifact deployed is identical to the one tested. Gives confidence.
Right, confidence is key. Now, we all know slow builds can absolutely kill momentum and developer morale.
Oh, definitely. Like wading through quicksand.
What are some game-changing optimizations to ensure builds are lightning fast and, ideally, simple?
Yeah, slow builds are a major bottleneck. If developers wait long for feedback, they context switch, get distracted, velocity drops.
So how do you speed them up?
A key best practice is keep builds fast. Strive for short build times. Martin Fowler's 10-minute build guideline is a well-known benchmark for a reason. Every minute trimmed compounds with frequent commits, freeing up valuable developer time. It's an investment that pays dividends.
Faster is better. What else?
Related to that, keep builds simple. Avoid unnecessary complexity in build scripts and processes. Simpler builds are easier to understand, maintain, debug. Complexity often leads to brittleness, slower performance, fragile pipelines.
Okay, fast and simple. Any other tricks?
And critically, leverage caching. Implement robust caching for dependencies and build outputs. Avoid redundant work. Docker's layer caching is excellent for this. Gradle's build cache too. Caching can dramatically speed up builds by reusing outputs where inputs haven't changed, like having ingredients prepped for the next meal.
Caching seems huge. Now let's get into specifics for popular tools like Maven or Gradle. Any expert tips that really move the needle?
This is where the rubber meets the road, yeah. Mastery of your build tools is crucial for CI/CD success. These aren't minor tweaks, they address fundamental pain points.
Okay, starting with Maven. Any tips for using it well in CI/CD?
For Maven and CI/CD, a couple of critical ones. First, use Maven Wrapper, MVNW. This is a true game changer for consistency. Ensures all developers and CI servers use the exact same Maven version. I've seen countless "it worked on my machine" issues vanish just by standardizing on MVNW. Eliminates inconsistencies from differing local Maven installs. Predictable, reproducible builds, like a universal version-controlled wrench.
That sounds incredibly useful. What else for Maven?
Also, isolate local repositories in CI. When running Maven in CI, configure each build job to use its own isolated local repo. Prevents builds using artifacts cached by other jobs. Ensures builds always validate against the central artifact repo. Catches problems with artifact management. Doesn't silently pass with stale dependencies.
Good point. And dependencies.
And effective dependency management. In multi-module projects, use the dependency management section in your parent POM. Centralizes and controls dependency versions, avoids conflicts, ensures all modules use consistent versions. Your single source of truth for dependencies.
Okay, great tips for Maven. What about Gradle?
Now, for Gradle in CI/CD, definitely utilize build cache, local and remote. Enable and configure Gradle's build cache. Local cache reuses task outputs on the same machine. Even better, a remote build cache shares cached outputs across different machines, devs, and CI agents. Dramatically speeds up builds across the whole team. Seen 15-minute builds drop under a minute with effective caching.
Wow, that's significant. Any other Gradle speed tips?
Enable configuration cache, another major speed booster. Stores the result of Gradle's configuration phase, allows Gradle to skip this phase entirely on subsequent builds if the config hasn't changed. Substantial improvements in build startup time, especially for complex projects.
Nice. And managing dependencies in Gradle.
Use version catalogs, libs.versions.toml, especially in multi-project builds or sharing versions. Centralizes dependency coordinates and versions, makes updates easier, ensures consistency, a structured, maintainable way to keep dependencies in check.
These tool-specific tips seem crucial.
They really are. They're not just minor tweaks. They address common pain points like inconsistent environments, dependency hell, slow builds. Without them, pipelines can be flaky, agonizingly slow, hard to maintain. Like, without Maven Wrapper, builds might work locally but fail in CI due to tool versions, breaking that fast feedback loop. Optimizing the build is critical to optimizing the entire CI/CD flow. Directly impacts developer happiness and delivery velocity.
Okay, so we've successfully built our software, hopefully reproducibly. We keep hearing this term artifact. What exactly is an artifact in this context, and why is managing it so critical in the CI/CD journey?
Right. Artifacts are essentially the tangible outputs of that build process we just talked about.
The finished product from the build stage.
Exactly. They are the final software components and packages created during continuous integration. Could be compiled binaries, libraries, Docker container images, packaged web apps, even configuration files sometimes. They are then consumed by the later stages, continuous delivery and deployment.
Got it. So why is managing them so important?
Well, the principle of build once, deploy many is absolutely fundamental here. An artifact should be built only a single time.
Only once.
Only once. Once built and verified in the CI phase, this immutable artifact, meaning it doesn't change, is then promoted through all of the environments. Dev, test, staging, and finally, production.
Why is that immutability so critical?
Because it ensures the exact same package that was rigorously tested is the one deployed to users. This eliminates any chance of inconsistencies arising from rebuilding the software for each environment. It solves that it worked in staging but broke in production issue, at least from the artifact perspective.
Oh, okay. Consistency again.
Exactly. It enables deployment consistency, leading to unparalleled stability and predictability across your environments. If the artifact is immutable, any environment-specific problem can be isolated to the environment itself, not the software package. Makes debugging much easier.
And rollbacks.
It also facilitates quick rollbacks. Properly versioned and stored artifacts are absolutely essential for rapidly reverting to a previous known stable version if a deployment introduces issues. You simply grab the last good artifact and deploy it, knowing it's exactly what was tested and worked before. It's your quick safety net.
Okay, so these artifacts are like the finished products in our software factory. Where do they live? How do we manage them centrally to ensure that consistency?
Good question. You need a dedicated artifact repository manager. Think of it as the highly organized, secure warehouse for all your software's finished components.
A central warehouse.
Exactly. It serves as centralized storage, acting as the single source of truth for all build artifacts generated by your CI process. This centralized approach simplifies access, management, and governance.
What are some common tools for this?
Popular tools include JFrog Artifactory, Sonatype Nexus Repository, and cloud solutions like AWS Code Artifact and Azure Artifacts.
And these tools do more than just store files, right?
Oh, definitely. A really powerful feature is proxying remote repositories. You configure your artifact repository to act as a proxy for external public repositories like Maven Central or npmjs.org.
Why would you do that?
Huge benefits. It caches external dependencies locally. This speeds up your builds by reducing network latency. It prevents builds from breaking if an external repo goes down, reduces reliance on external services, and, crucially, provides a control point for managing which third-party dependencies your teams can use, enhancing security.
Like your own private vetted stash of components.
Exactly. It's like having your own private, trusted stash of approved ingredients for your software
Yeah,
factory.
that makes sense.
Yeah.
Now, versioning. It sounds straightforward, but I imagine there are specific best practices to follow here, especially to maintain that immutability principle.
Absolutely. Consistency and meaning in versioning are critical for managing artifacts effectively, especially in a continuous delivery world.
So how should we version artifacts?
The widely adopted standard is semantic versioning, SEMVer. That's the major minor patch format like 1.2.3.
Right, major, minor patch. What does they signify again?
A major version increment indicates incompatible API changes. A minor version increment means new, backward-compatible functionality has been added. And a PASSH version increment indicates backward-compatible bug fixes. This standardized approach clearly communicates the nature of changes, allowing consumers to understand the impact of an upgrade at a glance.
Makes decisions easier.
Much simpler. Now, linked to versioning is that fundamental principle, the immutability of artifacts. Once a release artifact is published, it must never be modified or overwritten. Never.
Even for a tiny fix.
Even for a tiny fix. If changes are needed, a new version of the artifact must be created and published. This immutability guarantees that a specific version number always refers to the exact same set of bits, ensures reproducible builds, reliable deployments. Think of it like dating a specific edition of a book. If you say War and Peace, 1957 edition, you know exactly what you're getting. We need that certainty.
Okay, immutable versions. What else?
Finally, traceability is key. Each artifact version must be uniquely identifiable and traceable back to its specific source code commit, the CI build job that produced it, the tests that validated it.
How do you achieve that?
Artifacts should be tagged with relevant metadata build number, commit hash from version control, maybe the release environment, allows quick debugging and auditing if an issue arises with a deployed version. You need to know exactly where it came from.
Okay, that makes sense. And with these artifacts being passed around containing our actual software, security must be a huge concern for these repositories.
It's a critical attack vector, absolutely. Managing artifacts securely is paramount. They represent the software you're delivering.
So how do we protect them?
First, you need robust access control, RBAC. Implement role-based access control within your artifact repository. Ensure only authorized users, groups, or CI/CD service accounts have permissions to publish, consume, or delete artifacts from specific repos or paths. You wouldn't give everyone keys to the finished goods warehouse.
Right, least privilege. What else?
Next, vulnerability scanning. Integrate security scanning tools like JFrog X-Ray or Nexus Lifecycle directly with the repository or as part of the CI pipeline before artifacts get promoted.
Scan the artifacts themselves.
Yes. This helps prevent deployment of insecure software by flagging known vulnerabilities in your code or its dependencies before they reach production.
Okay, and dependencies.
This ties into dependency management. Ensure your builds pull dependencies from trusted managed repositories, often your own artifact repo acting as a proxy, not directly from unverified public sources. Protects against supply chain attacks where malicious code is injected via a compromised library.
Right.
Also maintains strict version control for all project dependencies. Pin them to specific versions using things like Maven's poms.xml or npm's package-lock.json, ensures reproducible builds, avoids issues from unexpected transitive dependency updates.
It really sounds like managing artifacts is more than just storage.
Oh, much more. The build once, deploy many, principal and centralized repositories are foundational, but the true significance lies in treating the pipeline as a critical part of your software supply chain.
The supply chain.
Yeah. If artifacts aren't correctly versioned, or an incorrect version gets deployed, it breaks the reliability chain. The system deployed might not match what was tested. It worked in staging issues. If artifacts aren't scanned, you could deploy code bundling insecure dependencies, creating security backdoors. If dependencies aren't from trusted sources, the build itself is vulnerable.
So artifact management is a control point.
A critical control point. For integrity, security, reproducibility, directly impacts compliance, quality assurance. Apply the same rigor to artifact repositories as you do to source code.
All right, let's talk testing. I've heard the term shift-left testing quite a bit in CI/CD contexts. What does that actually mean, and why is it so important for building confidence in our releases?
Shift left is a really important concept. It advocates for integrating testing as early as possible in the development lifecycle, not just tacking it on as a separate phase after development is done.
So testing earlier and more often.
Exactly. It's about continuous testing. Imagine building a house instead of waiting until the whole structure is up to check the foundation or plumbing.
You'd check as you go.
Right. You'd test the foundation before building the walls, test the walls before putting on the roof, test each piece as you lay it.
What's the main benefit of doing that?
Primarily early bug detection. Identifying and fixing defects early in the cycle is significantly less costly and time-consuming than finding them later in staging, or, much worse, in production.
Cheaper and faster to fix early.
Massively. It provides faster feedback to developers, letting them correct issues while the code is still fresh in their minds before it gets tangled up with other complex systems. Saves huge amounts of time and money.
So how is shift left implemented in CI/CD?
In CI/CD, this means automating tests to run on every code commit or pull request. This includes static code analysis, unit tests, often component-level integration tests, all providing immediate feedback at the earliest possible moment.
Okay, that makes sense. Now, the testing pyramid, that's a classic concept, isn't it?
It is, yeah, a very useful model.
How does it apply to a modern CI/CD pipeline? How does it help guide us in building this confidence engine you mentioned?
It absolutely applies, and it's a critical guide for allocating different automated tests to maximize efficiency and confidence. It suggests having a large base of fast, inexpensive unit tests.
The foundation of the pyramid.
Right. Then a smaller layer of slightly slower, more complex integration tests, and an even smaller layer at the top of slower, more expensive end-to-end tests. The idea is to catch the majority of issues with the fastest, cheapest tests at the bottom.
Okay, let's break that down. Unit tests first.
Right. At the broad base, unit tests. Purpose. Validate the smallest, isolated pieces of code, functions, methods, classes. Ensure they behave as expected. Like testing if each individual brick is solid. Placement. Very early in CI on every commit PR. Quickest feedback, best practices. Write testable code, small, isolatable units. Test early, often. Automate everything. Keep tests small, focused. Aim for high code coverage. Use mocking or stubbing to isolate the unit from external dependencies like databases or networks, keeping them fast and truly unit tests.
Okay, unit tests are the base. What's the next layer up?
Above unit tests are integration tests. Purpose. Verify interactions between components, modules, or services, ensuring they work together correctly, like checking if electrical wiring connects correctly at outlets. Do the pieces fit? Placement. After unit tests pass. On every commit PR, if fast enough, or maybe in triggered builds for longer suites. Strategy. For microservices, this could be API endpoint testing, checking message queue interactions, maybe using tools like test containers to spin up ephemeral databases in Docker for a clean test environment.
Got it. And at the very top?
At the very top, the narrowest part, are end-to-end E2B tests, also called system, acceptance, or functional tests. Purpose. Validate the entire application workflow from the user's perspective, simulating real user scenarios across all integrated systems, confirming business requirements are met, covering the full user journey, like testing if the whole house is livable, lights turn on, water flows, doors open, placement. Later in CI/CD, on fully deployed apps in staging pre-production. They're slower, more resource-intensive due to scope and UI interactions, so run less frequently. Best practices. Focus on key user paths, critical workflows. Keep test cases separate, independent. Manage test data effectively fresh. Isolated data is key. Poor test data causes flaky E2E tests. Automate them, though it's challenging.
It sounds like just having tests isn't enough. They need to be good tests.
Exactly. The mere presence of tests isn't sufficient. If tests are poorly designed, slow, or unreliable, especially flaky tests that pass and fail intermittently without code changes.
Oh, flaky tests are the worst.
They really are. They undermine CI/CD's agility, become a bottleneck. And flaky tests severely erode developer trust. People start ignoring failures. The pyramid offers a strategic approach. Catch most defects early with fast, cheap unit tests, reserving expensive, slower E2E tests for broader system interactions.
Balancing cost and risk.
Precisely. A mature CI/CD requires deliberate investment in a robust, efficient, automated testing strategy, designing for speed, reliability, maintainability, strategically placing them in the pipeline to optimize feedback without compromising critical coverage. It's a trade-off. The cost of testing versus the risk and cost of deploying faulty software.
So we got all these different types of tests running. How do we make sure they actually deliver on that promise of fast feedback, instead of becoming a new bottleneck themselves?
That's a critical point. The value is maximized with fast, reliable feedback. If tests run for hours, developers move on, the feedback loop breaks, productivity and confidence drop.
So how do we speed them up?
First, parallelize tests. Execute independent tests concurrently. Most CI/CD platforms support this. Can dramatically reduce overall suite execution time. Cut a 3-hour run down to 30 minutes maybe. Keeps devs engaged.
Okay, parallelization. What else?
Second, optimize test execution. Prioritize critical path tests first. Implement efficient test data management setup teardown. Minimize reliance on slow external dependencies in early stages using mocks, stubs, virtual services. Keep tests isolated, fast, deterministic.
Right. And the results.
Third, provide clear and actionable reports. Test results must be easy to understand. Clearly highlight failures with context logs, screenshots, error messages, so developers can quickly diagnose issues without digging endlessly. Vague errors waste time.
Makes sense. Notifications.
Fourth, enable automated notification. Configure the pipeline to immediately alert relevant devs or teams on failures via Slack, Teams, email. The moment something breaks, the right people should know instantly. Rapid response.
And
Finally, ensure continuous monitoring of test suite health. Track metrics about the tests themselves, flaky test frequency, long-running test execution time, overall test coverage. Addressing these maintains trustworthiness and efficiency. If tests are constantly flaky, developers stop trusting them, defeats the whole purpose.
Okay, deployment. This is really the moment of truth, isn't it? The final step, getting code into production. What's the overarching goal here? And how do we manage the inherent risks while still moving quickly?
It really is the moment of truth. The primary goal, our compass heading, is to release new software versions reliably and, crucially, with minimal disruption to users. A well-executed strategy is essential for delivering quickly and safely, and it absolutely must include robust provisions for easy rollbacks if issues pop up.
Confidence, control, user experience.
Exactly.
So let's dive into the different ways teams get their code out there. From the maybe simplest to the most advanced. What are the trade-offs with each approach?
Yeah, each strategy has its own set of trade-offs. You're balancing risk, downtime, complexity, costs.
Okay, what's the most basic one?
The most straightforward is probably all at once, sometimes called in place or recreate description. Basically, the new version replaces the old on all servers or instances simultaneously. The recreate variant even terminates all old instances before deploying the new one.
Sounds disruptive.
It is risk and downtime. It definitely incurs downtime during deployment because the application becomes unavailable. It's high risk. If the new version has issues, all users are affected immediately. Rollback means a full redeployment of the old version, causing more downtime. Often considered antiquated for modern high-availability systems.
So when would you use it?
Non-critical apps, maybe during scheduled maintenance, small-scale stuff where brief downtime is okay.
Got it. What's a step up from that?
Next, we have rolling updates, sometimes called ramped slow rollout. Description. The new version is gradually deployed across the server fleet, replacing old instances incrementally, maybe one by one or in batches like 20% at a time. Kubernetes has native support for this.
Sounds safer. Less downtime.
Yeah. Risk and downtime. Usually achieves zero or minimal downtime, as some instances are always available. Gradual rollout lets you monitor the new version on a subset before the whole fleet gets it. Less risky than all at once.
Any catches?
Well, during the deployment, both old and new versions run concurrently. This can cause transient errors or inconsistencies if they're not fully compatible, especially with database schema changes. Rollback can also be slower, instance by instance. Deployment takes longer overall.
Okay. Use cases.
Common for high availability apps where gradual updates are fine, especially good for stateless applications.
Moving up in complexity.
A more advanced strategy is blue-green deployments, sometimes called red-black. Description. You maintain two identical independent production environments. Blue, running the current stable version, green running the new one. Traffic goes to blue initially. Deploy the new version to green, test it thoroughly in isolation. Once verified, switch live traffic instantaneously from blue to green, usually via load balancer or DNS. Blue stays idle as an immediate rollback target.
Instant switch, instant rollback.
Pretty much. Risk and downtime. Achieves true zero downtime deployments. Rollback is very fast, and low risks just switch traffic back to blue. Allows comprehensive testing in a full production-like environment before users see it.
What's the downside? Seems ideal.
Cons. It's resource-intensive. Duplicate infrastructure means potentially doubling costs. Managing complex database schema changes and data sync between blue-green can be tricky and risky.
So cost and database changes are hurdles, Use cases.
Ideal for critical applications where zero downtime and rapid rollback are paramount, and the budget allows for the extra infrastructure.
Okay. What about canary releases? That sounds interesting.
Canary releases, yeah. Description. The new version is gradually rolled out to a small subset of users or servers, the canaries, while most traffic stays on the stable old version. Monitor the canary performance closely. If it's good, incrementally increase traffic to the new version.
Testing the waters with real users.
It's exactly. Risk and downtime. Allows early issue detection with real traffic but limited impact, only a small percentage exposed. Highly controlled risk mitigation. Enables testing in production safely, gathers valuable feedback before full rollout. Generally less expensive than blue-green, no full duplicate environment needed. Cons. Deployment process can be longer due to incremental phases. Needs sophisticated traffic routing and robust monitoring to track canary performance effectively. Potential for inconsistent user experience if versions differ significantly.
Use cases for canaries.
Best for large-scale, high-traffic apps where testing new features with a subset of real users is desired before full commitment.
And you mentioned feature flags earlier. How do they fit into deployment?
Feature flags are a critical control mechanism often used with these strategies. Description. You deploy new code to production with features or changes turned off using conditional toggles in the code. Then you enable these features for specific users or segments without a new code deployment. Fundamentally decouples code deployment from feature release.
Super flexible. Pros.
Enables very low-risk deployments. New code is initially dormant. Allows testing in production safely. Facilitates targeted rollouts, canaries, A/B testing, and crucially provides a quick kill switch to instantly disable a problematic feature by toggling the flag off, saving you from a full rollback sometimes.
Use cases.
Essential for trunk-based development, enabling canaries, A/B testing, gradual rollouts, and providing that emergency off switch.
Okay. Lots of options. But what happens when things do inevitably go wrong sometimes? How do we ensure we can quickly revert, hit that undo button?
That's a critical part of any robust strategy. The ability to reliably and quickly roll back to a previous stable state, it's your ultimate safety net, your deployment undo button.
Why is it so important? Seems obvious, but...
Its importance can't be overstated. Minimizes downtime, reduces impact of failures on users, and fundamentally builds confidence in the release process. Without reliable rollback, every deployment is a high-stakes gamble. People get scared to deploy.
So how do we make rollback reliable?
Ideally, automated rollback should be built into your pipeline, triggered automatically by failed health checks, monitoring alerts showing performance degradation, or high error rates post-deployment.
And how does it work with different strategies?
It varies. Blue-green is simplest and fastest. Switch traffic back to the old blue environment. Instant canary. Stop the progressive rollout. Revert traffic from canaries. Maybe disable the feature with its flag. Rolling updates involves redeploying the previous artifact version using the rolling mechanism, which can take time.
What about databases? Rollback seems scary there.
Yeah, database rollback considerations are inherently complex, often risky, potential for data loss or inconsistency. It's crucial to prefer roll-forward strategies where schema changes are backward compatible, meaning both old and new app versions can function with the updated schema simultaneously. A key best practice is decoupling DB schema changes from app code changes, deploying them separately, ensuring compatibility. Using version database migration scripts with tools like Flyway or Liquibase is essential.
And you have to test the rollback process itself.
Absolutely. Testing rollback procedures is crucial. An untested plan is unreliable. Regularly test rollback mechanisms as part of disaster recovery drills or pipeline validation. Don't wait for a production fire to find out your fire escape is blocked. Invest in resilience.
So clearly not a one-size-fits-all choice then. Picking the right strategy is nuanced.
Precisely. It depends on factors like application criticality, mission critical versus internal tool, tolerance for downtime, team maturity and skills. Advanced strategies need sophisticated automation ops expertise, infrastructure capabilities, can you do parallel environments, granular traffic routing, risk appetite, and desired release frequency.
So start simple, maybe?
Often advisable to start simpler and evolve. The progression from all at once to sophisticated canaries reflects a broader trend. Managing risk through smaller, incremental changes and rapid feedback, not big, risky releases.
And this ties into infrastructure.
Heavily. This shift is profoundly linked to mature infrastructure as code, IAC, and container orchestration. Advanced strategies like blue-green and canary depend on quickly provisioning, managing parallel environments, and sophisticated traffic routing. IUC automates environment provisioning. Kubernetes simplifies managing multiple versions and traffic patterns. Feature flags add another control layer.
So adopting these isn't just picking a technique.
No, it mirrors investment in foundational automation, infrastructure management, and a culture prioritizing minimal user impact. Without mature IAC and orchestration, trying advanced strategies can be error-prone, counterproductive.
Okay. Infrastructure as code ISE. That sounds like a real game changer for IT operations, fundamentally shifting how they work. What's the big idea here, and how does it plug into our CI/CD journey?
IAC has truly revolutionized infrastructure management, especially within CI/CD. The big idea is simple but profound. Treat infrastructure components, servers, networks, databases, load balancers as software.
Infrastructure is software?
Exactly. You define and manage it through code. Instead of manually clicking in a cloud console or running one-off scripts, you write a declarative configuration file describing your desired infrastructure state, extending software development principles to your whole infrastructure.
What are the key benefits of doing that in CI/CD?
The whole host of benefits. First, consistency and repeatability. IAC ensures environments dev, test, staging, prod are provisioned identically every time, drastically reduces configuration drift, those untracked manual changes causing inconsistencies and errors, guarantees production matches lower environments, eradicates it worked in staging for infrastructure issues.
Huge. What else?
Speed and efficiency. Automating infra provisioning via code eliminates time-consuming manual setup, reduces human error risk, a major source of downtime, dramatically accelerates the overall deployment process.
Deployments.
Version control for infrastructure. This is massive. Infra definitions stored in Git alongside application code. Full audit trail of changes, collaborative infra design via pull requests, easy rollbacks to previous known good infra states if needed.
Version control for everything, like you said before.
Exactly. Enhanced collaboration. When infra is code, ops and dev teams collaborate using familiar software practices. Code reviews, pull requests, shared repos for infra changes, blurs the traditional DevOps lines, fosters shared ownership.
DevOps in action.
Automated testing of infrastructure. Just like app code, infra code can be tested in the CI/CD pipeline. Linters, static analysis, integration tests to catch misconfigurations or policy violations before deploying the infra.
Testing the infrastructure itself.
Cool. And just-in-time provisioning. IAC enables dynamically provisioning resources only when needed. Spin up a test environment for a feature, use it, automatically tear it down, optimizes cloud costs significantly.
That sounds incredibly powerful.
Yeah.
So if IAC fundamentally changes how operations teams work,
Yeah.
how do you actually do IAC right within a CI/CD framework to maximize that potential?
Right. It's about seamless integration into the CI/CD flow. How do you make it work well? First and foremost, store IAC in version control. All your IAC files, Terraform configs, Ansible playbooks, CloudFormation templates must be in a VCS like Git. Fundamental for tracking, collaboration, rollbacks. Non-negotiable.
Okay, stored in Git, then what?
Focus on modularity and reusability. Design IAC configs in a modular way. Break down complex infra into smaller reusable modules or components. Terraform modules, Ansible roles. Promotes DRY. Don't repeat yourself. Simplifies updates, testing, makes code easier to maintain, understand.
Build reusable blocks.
Exactly. Then, a powerful integration approach is the GitOps approach.
Apps.
Yeah. The Git repository serves as the single source of truth for both application code and infrastructure definitions. Changes to infra are initiated by committing code Git, which triggers the CI/CD pipeline to automatically apply those changes. Often a pull-based model where infra converges on the desired state in Git.
So Git drives everything.
Pretty much. Provides versioning, audit trail, enhances security through pull-based deployments.
What about managing state? Tools like Terraform have state files.
Crucial point. For tools like Terraform, state management is vital. Use remote state backends like AWS S3 or Azure Blob Storage to store the state file. Allows shared access for teams and CI/CD systems. Ensures consistency. Also implement state locking to prevent concurrent modifications, which can corrupt state or cause inconsistencies.
Protect the state file. Got it.
And secrets.
And secure secrets and sensitive data. Paramount. Never hardcode sensitive info, API keys, passwords, certs directly in IAC templates. Use dedicated secret management tools, HashiCorp Vault, AWS Secrets Manager, integrate them with CI/CD to securely inject secrets at runtime.
Keep secrets out of code.
Absolutely. What's fascinating here is that integrating ISC into CI/CD really is a fundamental shift. It redefines ops roles, blurring DevOps boundaries.
Also,
When infra changes are code and automated, ops engineers adopt software practices writing, versioning, testing, deploying infra code. Developers gain visibility, can contribute to environments. GitOps epitomizes this convergence, this shared responsibility, common toolset, code, Git, pipelines, unified workflow. That's the heart of the DevOps cultural transformation. So it's more than just tools again.
Much more. Organizations neglecting to upskill teams in IAC or adapt structures for collaboration will struggle to realize the full benefits. It's an evolution of roles, skills, collaboration, not just adopting a new tool.
Okay, let's talk containers. Docker famously solved that infamous "it works on my machine" problem, which used to haunt so many developers.
Oh yeah, the classic headache.
How does that consistency benefit CI/CD specifically, and what's Docker's role now in these modern pipelines?
Docker fundamentally changed application packaging and running, and its core benefit for CI/CD is precisely that, ensuring environment consistency all the way from development to production. It virtually eliminates "it works on my machine" because the environment is defined within the Docker image itself.
So the environment travels with the code.
Exactly. The "works on my machine" problem is solved because Docker packages applications with all their dependencies, libraries, runtime, system tools, configs into standardized, isolated units called containers. These containers run consistently across different environments: developer laptops, CI servers, testing servers, production clusters. This consistency is paramount for reliable CI/CD. Minimizes environment-specific bugs, streamlines the whole workflow.
And they're lightweight too, right? Compared to VMs.
Remarkably lightweight and efficient. Unlike traditional VMs needing a full guest OS each time, containers share the host OS kernel. Makes them significantly lighter, much faster to start, more resource efficient, higher application density on the same hardware.
So what's Docker's specific role in the CI/CD pipeline?
It's multifaceted. First, building application images. Docker files define the precise steps to assemble an application image. This image becomes the primary immutable artifact for deployment.
The thing we deploy.
Right. Second, running tests in isolated environments. CI pipelines spin up Docker containers to run unit, integration, other tests in clean, consistent, isolated environments. Ensures tests are reliable, not affected by the CI agent state or leftover stuff.
Clean test runs every time.
Ideally, yes. And third, packaging applications for deployment. The built Docker image encapsulates the app and its runtime dependencies, makes it a portable, self-contained unit ready for deployment across pipeline stages.
Okay, that makes a lot of sense. So if Docker packages applications into these consistent units, Kubernetes then helps them, what? Dance together at scale? It's the orchestrator.
Exactly. Perfect analogy. While Docker provides the means to package consistently, Kubernetes is the open-source container orchestration platform that provides the stage and choreographs their dance. It automates deployment, scaling, load balancing, management of these containerized apps, especially in complex distributed environments.
So Kubernetes runs the containers. What's its role?
The role of Kubernetes is to provide that robust platform to run and manage these containerized applications reliably at scale.
And its benefits specifically for CI/CD.
Immense benefits. It offers automated deployments and rollbacks. Kubernetes has robust native mechanisms for deploying new versions and rolling back if issues occur. Natively supports rolling updates, configurable for blue-green, canary, makes those advanced strategies much more feasible.
Handles the deployment complexity.
Yeah, it ensures scalability and self-healing. Kubernetes automatically scales app instances, pods, up-down based on metrics, continuously monitors container node health, automatically restarts failed containers or reschedules them, ensures high availability, resilience.
Keeps things running.
Right. It leverages declarative configuration, IAC for K8s. The desired state of your apps and configs in Kubernetes is defined using declarative YAML manifests or Helm charts. Aligns perfectly with IAC principles, version control, repeatability, automating management of deployments.
Infrastructure as code for Kubernetes itself.
Exactly.
So bringing all three together, IAC, Docker, and Kubernetes, sounds incredibly powerful, like a complete system. How do we ensure they work in harmony to create that consistent, scalable delivery system?
It does create a potent stack for modern CI/CD, truly a consistency stack. But it requires adherence to specific best practices to ensure they work harmoniously and unlock their combined power.
Okay, what are some key practices?
First, strongly consider adopting GitOps for Kubernetes. Store all your Kubernetes manifests and Helm charts in Git. Use GitOps tools like Argo CD or Flex CD to continuously monitor Git and automatically sync the desired state with the actual cluster state.
Jet driving Kubernetes again.
Yes. Provides versioning, audit trail, enables automated pull-based deployments, enhances security and reliability.
Got it. What else?
Second, immutable image tags are non-negotiable. Always use unique immutable tags for Docker images, commit SHA, semantic version, never mutable tags like .latest.
Why is .latest so bad?
Because it changes what image it points to. Using immutable tags ensures a specific Kubernetes deployment manifest always refers to the exact same image version, critical for reproducible deployments and reliable rollbacks. If the tag changes meaning, you lose reproducibility and trust. Think specific book edition again.
Right, immutable tags.
Third, use Helm for managing Kubernetes applications. Helm packages Kubernetes manifests into reusable, versionable units called shards. Simplifies deployment, configuration, management of complex apps on K8s, allows templatized configs, easier upgrades, rollbacks.
Okay, Helm for packaging. Fourth,
separate clusters for different environments. For better isolation and risk management, use distinct Kubernetes clusters for dev, staging, production. Prevents issues in lower environments impacting critical production systems.
logical separation.
Exactly. And finally, adhere to security best practices. Integrate container image vulnerability scanning before deploying to Kubernetes. Implement Kubernetes network policies for traffic control. Use Kubernetes role-based access control, RBAC, for granular permissions. Securely manage secrets using Kubernetes secrets or external solutions like Vault.
Security woven in. It really sounds like Docker and Kubernetes are two sides of the same coin for consistency.
They are. The synergy is key. Docker solves, it works on my machine with packaging consistency. Kubernetes provides operational consistency and orchestration at runtime. Docker is pivotal during build test. Kubernetes ensures consistent, reliable runtime. IAC manages the K8s platform and deployments, often via GitOps, creates that consistency stack. App consistent in container, container consistent in orchestrator, orchestrator config, consistent as code.
And neglecting any layer breaks it.
Absolutely. Using mutable Docker tags, making manual K8s changes outside GitOps, poor IAC for the cluster. Any of these compromises the entire pipeline's integrity and predictability.
Okay, so we've got Dev and Ops working together smoothly with DevOps principles and CI/CD. Now we're adding seconds into the mix, creating DevSecOps. What does this actually mean for the pipeline, and why is it such a crucial evolution?
DevSecOps is a fundamental cultural shift, maybe even more so than DevOps initially was. It means integrating security practices and tools into every single phase of the software development lifecycle, especially within that automated CI/CD pipeline.
Not just at the end.
Definitely not. The goal is making security a shared responsibility, automating checks and addressing vulnerabilities early and continuously. Not as an afterthought, not as a final gate that blocks releases. Building security in, not bolting it on.
So what are the core principles driving DevSecOps?
Several core principles. First, shift left security. We mentioned this. Move security testing and considerations as early as possible in the process to the left on the timeline. The earlier vulnerabilities are found, the significantly easier, faster, cheaper they are to fix. Finding a flaw in the blueprint versus after the house is built.
Makes sense.
Second, automation. Automating security checks, vulnerability scanning, policy enforcement within the CI/CD pipeline is crucial. Manual reviews just can't keep pace with rapid CI/CD cycles. You need automated guards.
Keep up with the speed.
Right. Third, collaboration. Fostering close collaboration and communication between development, security, and operations teams. Security becomes shared responsibility. Devs are empowered to write secure code. Sec teams act as enablers, consultants, not just blockers saying no.
Breaking down more silos.
Exactly. And fourth, continuous feedback. Providing developers immediate, actionable feedback on security issues found by automated tools helps them learn and remediate quickly. Turn security into a continuous learning process, prevents repeating mistakes.
Okay, so it sounds like security tests need to be woven throughout the pipeline, not just one big scan at the end. What types of scanning are we talking about, and where do they typically fit?
You're right, it's about layers. A comprehensive DevSecOps strategy integrates various types of security testing tools at different pipeline stages, a multi-layered defense.
Okay, like what? What's first?
First, maybe earliest, is static application security testing. What it is. SAC tools analyze application source code, bytecode, or binary code without executing it. They look for known vulnerability patterns, common coding flaws like SQL injection, cross-site scripting, insecure coding practices. Think of it like a very smart spell checker for security flaws before you run the program. Placement. Very early. Pre-commit hooks, every commit PR, during build. Fast feedback on code issues right as they're written.
Okay, SAS checks the static code. What about running code?
That's dynamic application security testing, DAD.
Yeah.
what it is. Deus tools test a running application from the outside, simulating attacks to find runtime vulnerabilities, auth issues, session flaws, injection vulnerabilities that only appear when the app is running, like a simulated hacker probing your app. Placement. Later stages, after deployment to test staging environments where it can be actively probed.
Makes sense. What about dependencies? Open source libraries.
Critical area, that's software composition analysis, SCA, what it is. SCA tools identify all open source third-party components, dependencies, libraries used in your app. They check them against databases of known vulnerabilities, CVEs, and also check for license compliance issues. Placement. During dependency resolution in the build, after build by scanning artifacts or continuous monitoring of repos, ensures you're not pulling in known vulnerable libraries. Supply chain security.
Very important. And for containers?
For containerized environments, container image security scanning is a must. What it is. Scans Docker images for known vulnerabilities in the base image, OS packages, bundled dependencies within the image. Placement. After Docker image build, before pushing to registry or deploying to K8s.
Got it. And since we're doing infrastructure as code.
You need infrastructure as code, ISE. Security scanning, what it is. Analyzes ISE templates, Terraform, CloudFormation, K8s manifest for security misconfigurations, policy violations, potential vulnerabilities before the infra is provisioned. Secure by design for your infrastructure. Placement. Upon commit or before an apply operation in the pipeline.
Okay. And one more big risk area.
Secrets. So secret scanning, what it is. Searches for hard-coded sensitive info, API keys, passwords, tokens, private keys in source code, config files, commit history, a very common mistake. Placement. Pre-commit hooks to prevent committing secrets, or part of CI pipeline scanning every commit PR. Catch them before they escape.
Wow, that's a lot of scanning. Now, secrets, passwords, API keys, obviously super high risk. How do we keep them safe in an automated pipeline moving so fast? Hard coding seems like a terrible idea.
It's a terrible idea. Paramount to manage them securely. Hard coding secrets is a major unacceptable risk. If exposed, leads to unauthorized access, potentially catastrophic breaches.
So what's the best practice?
Use a dedicated secrets management solution. A system to store, manage, and securely inject secrets into applications and CI/CD jobs at runtime. Secrets are never directly in your code base or pipeline config.
What kind of tools are we talking about?
HashiCorp Vault is a leading example. Centralized secure storage, offers features like dynamic secrets, short-lived credentials generated on demand, automatically revoked after use, minimizes exposure window, fine-grained access control.
Cloud providers have options too, right?
Yes. Cloud provider solutions like AWS Secrets Manager, Azure Key Vault, Google Cloud Secret Manager offer seamless integration within their ecosystems.
Any general best practices for managing secrets, regardless of tool?
Definitely. Strictly limit access to the Secrets Manager. Regularly rotate encryption keys tokens. Enable and monitor audit logs. Use dynamic, short-lived secrets wherever possible. Ensure high availability and backup recovery for the secrets management system itself, its critical infrastructure.
Makes sense.
Yeah.
Now, with all these different scans, SAST, DAST, SCA, IAC, containers, secrets.
It's a lot of potential findings.
Exactly. How do teams handle that sheer volume without getting completely overwhelmed by alerts? Must be like drinking from a fire hose.
That's a very common challenge. Absolutely true. Security tools can produce a huge number of alerts, including false positives. Leads to alert fatigue, development teams get overwhelmed, critical issues get overlooked in the noise.
So how do you manage it effectively?
The best practice is a risk-based approach to prioritization. Don't treat all findings equally. Focus on issues that are genuinely exploitable, have significant potential business impact, and are actually reachable by attackers.
Prioritize the real risks.
Exactly. A low-severity vulnerability in dead code might be less critical than a medium-severity one in a core exposed API. Signal over noise. Some modern tools are getting better at automating this context-aware prioritization, too.
And how do you get developers to act on these findings?
Ensure workflow integration. Integrate security findings directly into developer workflows and issue tracking systems. Jira, ServiceNow, whatever they use. Vulnerabilities get assigned, tracked, remediated as part of the normal development process, not managed in some separate, siloed security system.
Treat security bugs like any other bug.
Essentially, yes. But successful DevSecOps hinges on more than just tooling. It requires that fundamental shift. Security teams as enablers, developers taking ownership. The volume of feedback can still overwhelm developers. If feedback isn't timely, actionable, accurately prioritized, it just becomes noise.
So the culture piece is key again.
Absolutely key. True effectiveness comes when developers are empowered to fix issues efficiently, maybe formally accept risk with justification, or mark false positives. Demands tools with clear remediation guidance and a security team shifting from bottleneck to expert resource. Without this cultural and operational evolution, sec becomes friction, devolves into dev versus sec versus ops, not true collaboration.
Okay, so we've gone through this whole process, designing the pipeline, building, testing, securing, deploying. After all that work, how do we actually know if our pipelines themselves are healthy and efficient? And maybe more importantly, how do we know our applications are performing as they should out there in the real world? This is where we need to truly see what's happening, right?
You're absolutely right. Monitoring, logging, and observability are not just nice to haves, they are absolutely indispensable for maintaining the health, efficiency, reliability of both the pipelines and the deployed applications.
It provides the necessary insights.
Exactly. Insights to detect issues, understand behavior, optimize performance, ensure alignment with business goals. It's the feedback loop for the entire system.
So what should we be monitoring, specifically for the pipeline itself?
For pipeline efficiency metrics, tracking certain indicators helps identify bottlenecks and areas for improvement. Build success rate, percentage of successful builds. A low rate might mean unstable code or flaky pipeline config. Needs attention.
Okay.
Build duration pipeline execution time, how long things take. Long duration, slow feedback loops hurt productivity. Those DORA metrics we mentioned earlier are key here too. Deployment frequency, agility, lead time for changes, overall efficiency, change failure rate, CFR, quality risk, and mean time to recovery, MTTR, resilience.
Right, tracking the DORA metrics for the pipeline.
Essential for understanding pipeline health and performance objectively.
And what about the application once it's deployed?
Application health in production needs rigorous monitoring too. Key things to watch. Error rates and types immediate insight into unexpected issues. Application response times, latency, crucial for user experience. Resource utilization, CPU, memory, disk I/O, network ensuring proper resource allocation, and ultimately user-facing availability and performance, the bottom line for your customers.
What kind of tools help with this monitoring?
There's a range. CI/CD platform dashboards often have built-in monitoring, GitLab, Jenkins, specialized solutions like Prometheus and Grafana, Datadog CI visibility, the ELK stack, Splunk, New Relic, and OpenTelemetry is emerging as a vendor-neutral standard for collecting this data.
Okay. Now, logs, they feel like the forensic trail when something goes wrong, giving us the step-by-step narrative of what happened.
Precisely. Logging is absolutely crucial for understanding what happened during a pipeline run or within a running application, especially for troubleshooting failures or doing postmortems. They are your detailed forensic trail, the story of execution.
So what are the best practices for logging effectively?
Good logging hygiene is important. First, implement comprehensive logging. Pipelines and apps should generate detailed logs with enough context, operations, sequence, decisions, errors. Don't be too sparse. Context is king for debugging quickly.
Okay.
Second, structured logging. Use a structured format like JSON, not just plain text. Far easier to parse, query, analyze by log management systems. Consistently include timestamps, service names, severity, correlation IDs.
Make searching easier.
Much easier. Third, centralized log management. Aggregate logs from all components, build agents, test runners, deploy tools, app instances into a central system. ELK stack, Splunk, Datadog logs provides a unified view. No more SSHing into individual servers hunting for logs.
A single pane of glass for logs.
Ideally. Fourth, log correlation, especially in microservices. Use correlation IDs, unique IDs, pass-through requests across services. Include this ID in every log entry for that request, lets you link log entries across services, trace issues end-to-end, crucial for distributed systems.
Trace the whole journey.
And finally, use actionable error messages. Clear, concise messages that help diagnose the problem without revealing sensitive data. No vague, something went wrong messages.
Got it. Now, beyond just monitoring basic health and collecting logs, we hear this term observability. What is observability exactly, and why is it considered the next level for understanding complex systems?
Observability goes beyond traditional monitoring. It provides a deeper understanding of a system's internal state based on its external outputs. While monitoring tells you if a system is working, is CPU high, is the site up, observability allows you to ask why it's behaving that way.
Asking why, not just what.
Exactly. It provides the tools to answer questions you didn't even know you had, to explore unknown unknowns. It typically relies on three crucial pillars.
Okay, the three pillars.
First, Logs, which we just discussed, those discrete time-stamped events capturing what happened at specific points, the narrative. Second, metrics. Aggregations of data over time, providing quantitative measurements. CPU utilization, request latency, error rates. The vital signs showing trends in overall health.
Okay, logs and metrics. What's the third?
Third, traces. These represent the end-to-end journey of a single request or transaction as it flows through multiple services in a distributed system. They show the path and the timing of each step, let you pinpoint exactly where latency or errors are introduced across a complex microservices architecture, like following a single package through the entire postal system.
Seeing the whole flow.
Precisely. By combining these three pillars, logs, metrics, and traces, you gain the ability to ask arbitrary questions about your system and understand why it's behaving a certain way, even for conditions you haven't predefined or anticipated. This is essential for debugging and optimizing today's complex distributed systems and is really a hallmark of truly mature CI/CD practices. Gives you that full, holistic view of your entire delivery pipeline and the applications it produces. Hashtag tech outro.
Wow, that was a truly comprehensive deep dive into CI/CD best practices. Really covered the gamut.
We covered a lot of ground.
From those foundational principles defining continuous integration and delivery, all the way through the intricate layers of modern deployment strategies, how security and infrastructure are woven in. It's crystal clear that CI/CD is so much more than just a set of tools.
Absolutely.
It's a philosophy, a culture, and definitely a pathway to delivering software with, well, unprecedented speed, reliability, and confidence. It's really about setting up your software and your teams for success.
Indeed. And if we connect this to the bigger picture, maybe zoom out a bit, it raises an important question for you, our listener, to think about.
Okay.
Given the strategic advantages of CI/CD, especially its profound impact on business agility and growth, how might the next evolution of these practices, perhaps driven by AI, machine learning, even more sophisticated automation, how might that fundamentally reshape the very definition of a software development team in the coming years?
Interesting.
What skills become paramount when the pipeline itself is hyper-intelligent? Maybe capable of self-optimization, even anticipating problems before they happen. It's a future we're kind of already starting to build.
We hope this deep dive has given you that shortcut to being well-informed, sparking those aha moments you were looking for.
Hopefully.
If you found this useful, or if you have more sources you'd like us to dive into on this or other topics, please reach out and share them with us. We'd love exploring these things with you.
We do.
Until next time, keep learning, keep building, and keep delivering.